Well, thank you all for being here. I know it's a small audience, but hopefully other people will join after the coffee break. It's the last day of the conference, so of course a lot of people are tired. But let's hope that we're going to make it as interactive as possible. We have great conversation. And the idea of this workshop that we wanted to organize is, this is the first edition. And although a lot of people are working on privacy, which is amazing, and the community is getting larger and a lot of topics are being explored, we felt like metadata privacy is one of the topics that everyone is acknowledging how important it is, but we're kind of hitting a plateau in terms of papers, in terms of systems building, and no system really have reached a large scale, and it's being deployed and used by a lot of people, even though, again, renowned cryptographers such as Phil Rogaway and Whitfield Diffie, they're all acknowledging how important the metadata is. So we were hoping to gather the community. We can discuss the metadata privacy. We can discuss open questions and challenges. And hopefully in a few years, we're kind of hit like the next big breakthrough in this important issue. Without further ado, I'm very, very happy to have Sofia Celi as the first keynote speaker. I think a lot of you know her. Sofia worked, she's known for her amazing cryptographic work, but she also does a lot of privacy and a lot of expert consultation with the UN. She has been she's received multiple awards, and she actually received an award here at this symposium this week. So congratulations, Sofia. I'm very much looking forward for your talk, and yeah, the floor is yours.
Yes, thank you very much for that kind introduction, and hopefully next year I will be there. But yeah, today I wanted to talk to you about a specific cryptographic scheme that, while it's not specifically usually targeted to what it is metadata, sometimes some of the kind of like things that this scheme wants to actually encrypt is usually not the purpose of the network communication or of the secure messaging protocols. So it's kind of like an alternative thing that also wants to preserve the privacy, but not for the usual network protocols that we usually think about. And this hopefully will make itself clear during the talk. So today what I'm going to be talking about is private information retrieval, and we are going to be talking about these foundations, some of the current research that is currently happening, and also some future directions, specifically when we actually want to achieve privacy for systems as, for example, search engines and recommendation-based systems. And if you're interested in my work, I have also put a link to my website on this slide. Okay, so just to give you again an outline, this is going to be not much of a really depth technical explanation of how PIR works, although we will see some of the cryptography, but it's not the main purpose of the talk. But rather what I'm going to be sharing with you is kind of some thoughts of what actually means to add privacy to the queries that we send to databases. And for this, we're going to be first start looking at what private information retrieval or PIR is, specifically in the single server case, and also in the index-based and later keyword case-based, and also by using a specific mathematical construction that is called lattices. And once we have actually that definition and maybe start looking at some specific schemes that are deemed to be efficient currently, we were going to be trying to answer the question if indeed these current schemes that exist in the research literature currently are able to handle complex systems, and if they can be used now for recommendation system and for search engines. Okay, so just to set the scene, why we want to talk about this is because one of the things that we use the most when we're actually having communications over the internet is a database. So think about the most easy example. If you want to access a specific service, sometimes you're asked to log in or to register. And in order to do that, you most often than not have to use a database, because that database is the one that is going to be having a storing your credentials and later either retrieving those credentials or checking that those credentials exist in that specific place. And that specific place is indeed a database. So the majority of times we're going to be using database to query and check that specific credentials exist in this specific place. But it turns out that databases are more than just for querying single elements. They are indeed used in other types of systems because they allow for recommendation-based systems that are based on that specific query. So think about, for example, when you're actually typing in a specific query on a search engine, you're eventually talking with a database, a really big database that contains all of the elements of the web that is going to give you like the most accurate response in regards to a query. They're also used sometimes for transparency means, so they're heavily used in the TLS setting when actually you're checking if your certificate has been compromised, or if you're checking that the website is not malicious for whatever definition is the malicious when you're using something as the safe browsing API. But of course, when we're using all of these systems, we're incurring a lot of privacy violations, because it turns out that when you're actually launching these queries, you're revealing a lot about yourself in these queries. Especially when you're working on search engines, you're revealing quite a lot about what you're interested in, what you're currently doing, maybe where your location, because many things can actually be inferred from that specific query that you launch it against a search engine. And in the case of, for example, credential checking systems, you're also sometimes revealing the browser history of a user over time, because, for example, let's say in the TLS setting, if you're using certificate transparency and you're indeed launching a query to check if a certificate is indeed logged in the certificate transparency logs, by doing that specific system to preserve security, at the same time, you're having a privacy violation because you're revealing the browsing history over time to this third-party service, which is the certificate transparency logs. So maybe with these two examples, you will see that even though it's not a network protocol or it's a secure messaging protocol, we're still incurring a lot of privacy violations because of the specific queries that we're sending against databases. So one of the questions that we have been doing in the work is how can we integrate privacy into these specific queries that we send to databases. And we can start with a simple version of the problem, just looking at the most basic scheme, in which what you have is that you have a server that is going to be holding the database, and this database is assumed to be an array of M elements, and is indexed by the digits, which are the position of the elements in that specific array. So a simple definition of this problem will be let's maybe add privacy to a single query that we launch into this very simple representation of a database. After that, what we can do is expand it to handle batches. So for example, ANDs, multiple queries that you send against this public database. Then you can also expand so that the structure of this database is no longer just one that is index-based, but also that is one that is, for example, keyword-based. So you have key value maps. And then you can even expand it for more complex operations, maybe for joins and disjoins, maybe to handle distributed database systems in what you want is the AND of different databases that exist in some place. You also maybe want to expand for more complex algorithms, so not only a specifically query for a single element on that specific database, but for the closest element or for X closest elements to that specific query that the user sent. So obliviously navigating the database to finding similar or close elements to that specific query. And eventually, you also want to expand to not only work with public database, but also private database that sometimes hold really sensitive information or that are private because of some copyright restrictions. So we also want to expand the model to not only handle public databases. So currently in the research, we actually have some efficient schemes for the three points that I have highlighted here, but we're still really struggling and kind of studying some research to actually handle all of these other more complex cases. And one of the points of this presentation will be how can we do that? Can we actually arrive to one solution that fits them all? Or actually what we should start looking from a research and practical perspective is actually a different solution that handle all of these different cases. And of course, here at the end, I have put also a question of, is that all? Because maybe this is like a little bit of a snapshot or a description of the current state of the art, of the current state of these practical kind of questions, but maybe they are not all of them. So I encourage you to also look at other kind of questions that might be here in the database systems. Okay, so with that, maybe let's start discussing one specific scheme that indeed arrives or gives you kind of some kind of privacy when you're actually launching queries against database. And this specific scheme is usually called Private Information Retrieval or PIR, which gives you the ability to retrieve items from an online public database of M elements without revealing anything about these specific queries. And it is assumed that this database is both public and is hosted by a server or sometimes by a collection of servers. It is a very simple scheme because essentially what you have is that you have an X amount number of clients and you have a server or a coalition of servers that are the one that is going to be having this specific database. And the steps are very simple. You just send a query, the server replies with a response to that specific query, and with high probability, you as a client will be able to pass that response and get the value associated with the query. And this is, if you're familiar with all the different topics in computer science, you will see that this is a subset of information retrieval, with the caveat that we're trying to add privacy to information retrieval. It is a very active area of research because you will see every day in the archive repositories that is at least there's one paper that is published about PIR. So this is a very active research area. There's some promising efficiency of some of the schemes that we're going to be seeing. And there's also so many other ideas of how to make them even more efficient, both from a software, hardware, and also complexity perspective. So there's a lot of promises over there. And there's a variety of applications, as I already have talked a little bit in the previous slides. What is going to be the baseline of this talk? We're going to be looking at single server PIR, because as I told you in some previous slide, you have kind of two versions of these PIR schemes. You have ones that you use a single server, and you have others in what you have is a multiple servers that are going to be handling the queries. We actually chose just single server PIR in a semi-honest setting. And again, as I told you, the database is assumed to be public, and sometimes these schemes are going to be involving a thing that is called an offline preprocessing phase that is created in order to reduce some of the cost of the scheme. So why we decided to go for single server PIR, which could be one of your questions, essentially because we think this is the paradigm that is the easier to actually deploy and put into practical terms. Why? Because multi-server PIR is usually based in information theoretical guarantees, which is great, but it is difficult to actually find out in the real world. It's actually these servers that actually will not be colluding to each other to actually preserve the privacy. And sometimes there has been some questions that even from a legal or practical perspective, it is really difficult to find these servers, because imagine, for example, if you have a server in a certain region of the world that has a stronger privacy legal frameworks than other region of the world, does that mean that that encrypted or private constrained representation of the data of those specific users will have to have different legal frameworks depending on where the server is based? So it is unclear what specific legal considerations we should have with multi-server PIR, as well as actually practical considerations of actually putting in the real world. So we decided to look on single server PIR because it's the one that seems the most adequate or more simple to actually deploy, and also because the efficiency of that specific type of a scheme seems to be improving. And it also allows for small organizations to use it. So you no longer need like a coalition of different companies or different organizations trying to preserve the privacy, but rather we wanted to create something that even small organizations can have. If they just have like a specific instance of a server, they can easily just use, instead of having to create all of the legal framework to actually have multiple server PIR. And of course, single server PIR is based on a thing that is called computational assumptions. And this is already well known in the literature and also from a practical perspective. So actually believing those specific assumptions would not be hard from a practical and real world perspective, because we already believe in them in the many places that we use encryption. Okay, and the one that is more efficient, or currently that is think as the more efficient, more practical one, is what is called lattice-based PIR. And essentially what we do here is that, as I told you, we use a computational assumption, and that specific computational assumption that we're going to be using is some hard mathematical problems that are based on lattices. And essentially we use two specific problems from that specific mathematical literature. We use the learning with errors problems or the ring with learning with errors problems. And essentially those are just hard mathematical problems that you can construct over lattices. And in order to make them more efficient, we actually have like a mode in which what we call those schemes to be stateful, because we're going to be pre-processing a lot of the parameters ahead of time. So when we actually launch the queries as clients, the complexity of the computational times are going to be less, because we computed ahead of time a lot of the parameters that were needed. There's other schemes that are based on other computational assumptions that are also efficient, but these are the ones that we consider the most practical and efficient, because it's really easy to explain to engineers and also from an implementation perspective to actually have these schemes deployed. So they are practical from both because they arrive to really great efficiency, and also because they are really easy to convey when you're talking with engineering teams or when you're actually wanting to have a practical implementation of them. Okay, And what do they rely? They rely on a thing that is called additive homomorphic encryption, which is essentially a way in which we do is that we create a long indicator vector, which is as long as the number of elements in the database, and we put a 1 on the specific element that we're interested in. So for example, let's say that you know that your element in the database exists on the first slot of the database, in the first slot of the database, you create a long indicator vector with a 1 on that specific position. And then you encrypt that specific vector so that later the server receives this specific vector and performs a matrix multiplication, a vector to matrix multiplication, but homomorphically. So that when you actually get that specific vector returned to the client is able to open it up because they know the keys associated with that encryption algorithm, and they are able to actually know the value associated with that index that you just queried for. And again, as I told you, this is based on additively homomorphic encryption. So you could do all of these operations that you need in order to get that specific element from the database by leveraging the fact that it's homomorphic encryption. And the newer efficient schemes that exist in the literature are directly based on this specific notion. And the most efficient ones and most practical ones are Fredo PAR and Simple PAR. Those are kind of the same scheme. They just different in some specific instantiations, as we will see, but they are just essentially based on lattices. And then again, they are very efficient, as you will see in the next slides. And they are also very practical because it's really easy for them to be deployed, because if you go to some engineering teams and actually explain them how the scheme works, it is easy to understand, which is always great for cryptography, because if you can actually convey how a specific cryptographic scheme works to engineers or to production teams, then it's much more easier to get it deployed. And also from an implementation perspective, it is very simple to implement because, as you will see, it only involves vector to matrix multiplications or matrix to matrix multiplications. So it's really easy to do this because we have a lot of systems that already do those specific type of computations. Okay, so essentially what we're first looking at in this specific talk is this scheme that is based on lattices that is called Fredo PAR. And because people always ask me about why it's called Fredo PAR, I'll explain why it's called Fredo PAR. It's essentially because it's based on another scheme that was submitted to the post-quantum NIST competition, to the post-quantum NIST process. It was not selected as a candidate to be standardized, but I think it's currently standardized by the German government. But that scheme is called FredoChem. And the reason why it's called FredoChem is because instead of being based on ring learning with errors, it is based on pure learning with errors. So you kind of toss the ring. So that's why it's called Fredo. Because Frodo also kind of eventually at the end of the Lord of the Rings, they also toss the ring. So here you are tossing the ring. And because we're based kind of in the same mathematical idea, we also call our scheme Fredo PAR. As I told you, this is really similar to another scheme that concurrently was discovered in the literature that is called Simple PAR. And if you want to read about those two schemes, I have put the links on these slides as well. Okay. So as I told you, essentially, this is a single server, lattice-based, because we're using the LWE problem, index-based PAR. So in this case, imagine that the database is an array of M elements, and those specific elements are indexed with the position of those elements in the array. So it's essentially indexed by digits. As I told you, essentially what we're going to be using is kind of like a pre-processing model in order to save kind of some efficiency. So this scheme is going to be having two subphases, one pre-processing phase and also one online phase. The online phase is essentially the phase in what it happens is that the client indeed launches the query to the server and the server replies with the correct answer. But let's first start looking at the offline phase. In the offline phase, as I told you, what we're going to be doing is what we're going to be pre-computing some parameters ahead of time. So what parameters are we going to be pre-computing? The first thing that we're going to be doing is that we're going to be representing the database as a matrix. And the way that you define the dimensions of this specific matrix depends on your specific implementation. Sometimes you can use a thing that is called a square root encoding, which is essentially that the dimension of the matrix is going to be the square root of M times the square root of M, which is essentially, M is essentially the number of elements in the database. But the core idea is that you represent your database in a matrix-like structure. Then what you do is that you generate a seed, and from that seed you expand and you generate a matrix that is based on that specific seed. You multiply A times the matrix representation of the database, and you get this result M, which essentially is kind of like a hint of the database. why we do this is because we don't want the clients to download the whole database, right? Because if you download the whole database, that will incur in a lot of computation, a lot of communication complexity, because these databases are really big. So we don't want clients to do that. But on the contrary, what we want is that clients kind of like download a hint, a smaller hint in regards to that specific database. So whatever this value M, which is a matrix, is going to be smaller than the original database, but it's kind of like a hint that will allow the client in order to later launch the queries against the specific database. Okay, and the server does this, and the server makes it public, these parameters. So the server is going to make public both the seed and also this specific hint that belongs to the database. Okay, and then the server is going to do this once, and eventually for an X amount of queries, those parameters are going to be remaining the same. So for example, let's say that a client launches 2 to the 32 queries. Those 2 to the 32 queries are going to be using these same preprocessing parameters until they reach this specific limit, and then the server will have to redo this preprocessing again. But maybe intuitively you see that you're saving a lot of time because essentially you are able to reuse those parameters for a really big number of queries that the clients can launch. The client optionally can also have a local preprocessing phase, and this depends on how constrained are you. So if you're really constrained on a space, we often recommend that you don't do this preprocessing step. But if you have some memory space, you could indeed, as a client, also launch this client preprocessing stage. Essentially, what we do here as a client is we're going to be creating 2 parameters, B and C. If you're familiar with LWE, this really looks like LWE because essentially what you're going to be doing is that you're going to be sampling some 2 elements, a secret element that we call S and an error element what we call E. And they're sampled from a specific distribution. You multiply this vector S times the expanded matrix representation, which is A, plus the error, which is classic LWE, and you get this vector that is called B. And you do something similar with C, which is essentially the multiplication or the vector to matrix multiplication between S and M. And you have these parameters now stored in your local memory, these parameters B and C. And you can derive X amount of these parameters. So you could have XBs and XCs. Okay. You do that as a server and a client, and those parameters are going to be kind of hold the same for 2 to the 32 queries, for example, that eventually the client will send. Okay, now that you have performed this preprocessing phase, you're ready to launch the query. So how do you launch the query? Essentially, what you do is that you construct, as I told you, this long indicator vector, and you put a 1 on the specific position that you're interested in that specific database. You do an addition of the B plus this a popped B that you just popped from the local storage, you add this specific vector with the indicator vector, and you send this B prime to the server. The server, in terms, what it does is that it multiplies this B prime, this vector, times the matrix representation of the database to get a response that is called C prime. And the client, once it receives C prime with high probability, is going to be able to subtract C prime minus C and get back the specific value associated with the database. Now, if you already asked me from an implementation perspective if this is practical, from the client side, you maybe already can see why this is practical. Because essentially from an implementation perspective, we only incur on 1 addition and 1 subtraction, which is great because we're essentially just doing vector addition and vector subtraction that is really easy to implement, and it's also very it's not computationally heavy to actually implement that. From the server's perspective, you do have kind of like a computationally heavy operation because we have a vector times matrix multiplication. But because the server usually has more computational power, we assume that that is okay. What we wanted to create with this scheme is something that is really easy for clients to launch because those are the ones that actually are constrained on resources, while we assume that the server has more computational power. From a communicational perspective, it's also great because we only send over the wire a vector, another vector, and that's all. So it's essentially great. Why we arrived to this is because, as you remember, we did a bunch of the computation ahead of time. So all of the heavy matrix-to-matrix multiplications or some of the vector-to-matrix multiplications are done ahead of time for an X amount of queries that later can be launched. Okay, And how did these ideas originate? Essentially, this is because people sometimes ask me, how did we come up with this specific idea? It's because we were actually reviewing some encryption papers, essentially ones authored by regex. So this is very similar, and indeed is the same almost as regex encryption, if you're familiar with. In regex encryption, you have essentially that. You have this specific parameter A multiplied with the secret plus the error plus just a specific mu. And this is essentially what we did in front of PIR. But what we realized is that instead of having to do this all the time, every time that you launch a query, that you can pre-process a lot of these parameters ahead of time, and then just add your indicator vector where with the specific position that you're interested in the database. So that's essentially the core idea that we had, and that we can move a lot of this computation ahead of time, and that it can stay the same, and the security holds if it stays the same for X amount of queries that the client can launch. But sometimes here that you can still, or you can start asking me, I think, is what happens if the database changes? So this scheme actually works quite perfectly if the database remains static for a big amount and period of time. Because let's say now that your database changes because you added elements or you removed elements or your elements were updated in place, then you will have to redo this preprocessing phase, because this preprocessing phase is really tied up to the matrix representation of the database. So if your database changes, then all of your preprocessing phase will have to change again because your database changed, which is not great, as we will see next, because some search engines or recommendation systems really work with databases that are rapidly updated. Okay, and why this idea original is because it was really informed by practice. We wanted to be able to use something that could run in the browser, and hence it was not so complex from a client perspective to be implemented. And we wanted to use something that works even if we have constrained resources from the client perspective. We also wanted to work with moderate sizes of databases. So you will see next in some numbers that this actually works great when you have moderate sizes of databases, because we wanted to actually use them in credential checking systems. So for example, if you wanted to check that your password is not present or is present in a linked database of passwords, then you could use that. And those databases are actually not that big, so you could use this kind of a scheme. And we also wanted to have a system that works even for smaller organizations. We didn't want to have a system that needed like many organizations to be collaborating with other servers of big organizations, or servers that needed a lot of computational power. We wanted something that could be used by small organizations. And as you see here in the scheme, essentially you arrive at great computational times from the client perspective. Okay, and if you want to actually see numbers from the numbers perspective, if you see at the query and the passing times, you will see that we arrive at milliseconds for the client. There is a little bit of more computational complexity from the server side, right, in the response. It's a little bit more heavy from the server, but from the client perspective, it's really great. And if we have, for example, databases of the size 2 to the 20 elements, and each element is of 124 bytes, then we actually arrive to really great times. Something interesting, if you're interested in from a research perspective, it turns out that if we make the elements, each element in the database longer, then we no longer have that much great times. So you will see here that then the passing algorithm from the client perspective, when the elements are really big, is no longer that great because we have really long elements. So it seems that this scheme really works for really long number of elements in the database, but not so much when those elements are really big. So if you're interested in research, that is something that you can look at and actually create a PRS scheme that works well for both the number of elements in the database and the sizes of the elements in those specific databases. Also to note here, these databases are essentially assuming that each element in the database is of the same size, which again, maybe doesn't match from a real world perspective, because if you're familiar with databases, you know that usually not all elements in a database are of the same size. But that is the assumption here. So in practice, this is great. We have really great efficiency. We can work with public databases. We can work with databases that are structured in a way that the index is a digit. But if you're familiar again with real-world systems, you will know that databases are not structured always in this simple way. For example, sometimes they are indexed by keywords. So think about the most simple database in which you have is a username database. They will be indexed by the username, and then the value will be, for example, the email address, the encrypted password, anything like that. So usually they are not indexed by digits. And they're also usually not a structure in this simple way in which you have an array. They're usually structured as JSON or graphs or Excel spreadsheets. Also, the queries that we're interested in the real world are usually not so simple. So it's not usually that we launch a query for a specific element that exists in the database, but usually we're interested in more complex queries. We want and or statements. We want the combination of database systems. Sometimes we want approximate nearest neighbor elements to that specific query. And also databases are constantly updated. As I hinted to you here, this scheme no longer works quite well when the database rapidly changes because all of the savings that you had in the pre-processing phase are no longer applicable because your database is always changing. So this doesn't work if your database is highly updatable. And is the security enough? So at this time, I explained to you a scheme that essentially works with a public database. But what about if the database is private? What about if you want to actually have assurance that the server didn't change the database or didn't change a specific row in the database in order to trick you? In those cases, for example, you could add a zero-knowledge proof or some kind of commitment scheme in order to assume a stronger notion of security. But as you see here, while this is a great direction of a scheme, in practice, this might not be enough. But what we can do with these kind of schemes is that they are highly flexible. So we can start expanding on these schemes and trying to actually be able to solve some of the other practical problems that I just put in the previous slides. So for example, we can adapt this index-based PIR scheme into something as a keyword-based PIR scheme. So what we do is that instead of only working with this structure of the database that is assumed to be an M array of elements in which each position of the element is the index, what we can have is other types of databases that are essentially key value maps. How can you do that? Is that we could use LWE single server index-based PIR schemes, that's the ones that I just presented, and leverage the fact that we already have efficient key value filters that allows us to map keys into values. And these are really small data structures that we could use in order to create these keyword-based PIR schemes. So what we did is that we merged LWE-based single PIR schemes with key value filters. The first thing that we did in this research was actually trying to look at the current state of the art on filters structures to actually find out what is the most efficient and most cost-effective filter structure that we could use. And we found out that the most efficient and state-of-the-art filter is one that is called binary fuse filters that is very similar to a XOR filter or also to a Bloom filter. It essentially works the same as a Bloom filter, but instead of putting a 1 on the position that the filter gives you to the specific element, what you put there is the result of a fingerprint function. And this fingerprint function essentially is a randomly chosen hash function. Okay, so you're going to be having this filter, and then you're going to be having X amount of hashes. Let's say that you have 3 hashes. Those hashes are going to be giving you the position that that specific element is going to be stored at that specific filter. So your element is X, and let's say that you have 3 hashes. Then the hash of X gives you the first position. The hash of X, the second hash gives you the second position, and the third hash gives you the second position. And instead of putting a 1, as you do in Bloom filters, what you do is that you put the result of this fingerprint function. And essentially, if you later want to retrieve an element, what you do is that you do the XOR of those specific elements, and it should be equal to the fingerprint function. Another interesting thing of these new filter-like structures is that you will see that you segment the filters into these specific segments. So those specific hash functions map to specific segments in the filter. Okay, so essentially what we did in PIR is that now we have this really efficient filter-like structure. What we kind of questions ourselves is how we can actually map these key value pairs into this specific filter structure. And it's really simple. What we essentially did is what a filter does, which is essentially just hash the specific key concatenated with the value and find those positions in the filter where these specific elements are going to be mapping. Of course, here, if you're already familiar with filters, you will know that now we have kind of like a blow-up factor, right? Because no longer your filter is going to be the same size as the original database. It's not going to be longer M, but rather we're going to blow it up because we're also introducing an X amount of hash functions that map to the specific position. So in this case, you will have a constant space blow-up depending on the number of hash functions that you're going to be choosing. But it's not so bad, and indeed, this parameter is called Celi, and it's usually approximate 1.08 or 1.13, depending on the number of hash functions that you choose. So it's not so bad. But essentially what we're going to be having is kind of this array that's a filter, which is essentially going to be having n elements, which is just a multiplication of the original m elements of the database array, plus the blow-up times the blow-up factor that you just introduced because of the filter. Okay, and if you are doubting me that these filters are the most efficient one, the original paper that introduced this filter shows us that both from a space perspective, from a memory perspective, and also from a query times perspective, the filters, this specific filter construction is much more efficient if you compare them with XOR filters, with cuckoo filters, or with Bloom filters. And if you see in these graphs, the binary fuse filters are the one highlighted with green and these brown. And as you see, those are the ones that actually arrive to the better complexities. Okay, so what we did now in PIR is that now we're going to be storing in this specific filter structure these specific keys concatenated with the values, and the filter is going to give us the position in which these specific key value pairs are going to be mapped. We didn't want to blow up the filter because if you think about it, those key concatenated with values elements are going to be really long. We didn't want to blow up the single filter to actually handle this. But what we decided to do is create the amount of filters that are concatenated together. And each one of those concatenated filters are going to be having segments of those specific elements. And that is great because if you think about it, and if we structure in that way that specific filter, we're going to be studying to having, again, a matrix, which is great for LWE-based PIR schemes because as we saw in the previous slides, they essentially work in matrices. So now we're going to be having concatenated filters, and the filter is going to give you the position of those specific elements on the filter. And that's what we did. What we did is that we did a combination of these filters with the LWE-based protocol. So the original database is going to be this raw key value map, as you see here, keys associated with the values. We're going to take those keys associated with the values and represent them in a filter by using binary fuse filters. The filter is going to give us the position that those specific elements exist in the filter, concatenate those filters as a matrix, and then use that matrix representation to perform the LWA-based PIR scheme that I showed you in the previous slide. The only difference will be that instead of sending this indicator vector with only a 1 on the position of the specific element, now we put a 1 on the specific position that the hash functions of the filter is going to give us to find the element on that specific filter. And if you actually compare with index-based PIR, you will see that we almost have minimal overhead, both from the communicational and computational complexity. So you will see here that we incur on a minimal difference when we're actually adding these filters, because it turns out that this filter structure is very efficient. Okay, so coming back to the previous slide, now we have maybe something that is efficient and actually works with databases that are indexed by keywords. But all of the other questions that exist in these slides have not been answered. What we have is an efficient index-based or keyword-based PIR scheme that works with a public or a static database, but everything else remains unanswered. So maybe now at the remaining time of the talk, let's start looking at some actual applications and see if indeed these LWE index-based or keyword-based PIR schemes will work with this kind of other applications. So as I said at the beginning in some slides, is that one of the most used applications of information retrieval and also of databases is to be used on recommendation systems. And recommendation systems are either the most classic ones, for example, music recommendations, news recommendations, image recommendations, or the search engines in itself can be thought of as recommendation systems. And it turns out that contrary to, for example, a system in which what you're doing is checking if your password exists in a leaked database of passwords, it turns out that in recommendation systems, users want accurate and almost near instantaneous responses. So when you actually type a query in your favorite search engine, you will almost immediately expect the search engine to ask you. So there's no time in which you could be waiting or having this process to actually run in an offline mode. You cannot do that because users usually expect almost immediate answers. How does it usually look like in practice is that these engines usually hold a catalog or a snapshot, and they are constantly updated. So if you ever work with any recommendation system, let's say a music recommendation system, you will see that that catalog is constantly updated. The rows change, the rows are added or removed. And these are really big databases as well. So for example, for search engines, it is sometimes thought, but that's an approximate number, that those databases are around 100 and 200 petabytes. So you see previously that I showed you some numbers for moderate sizes of databases. These are really big databases, the ones that are used by recommendation systems. So let's start looking at one specific one. Like, for example, let's start looking at search engines. One study from 2004 actually found out that new pages are created at a rate of 100% per week. 20 million new pages are added every week, and roughly 3.8 terabytes in size are added every week. And only 20% of pages available today will still be accessible after 1 year, so there's a high removal here. But after a year, about 50% of the content of the web is new. So there's minor changes in place, but there's a lot of changes on the database of additions and removals. So this is a database that changes quite rapidly in its size, right? Because a lot of elements are added and removed, but there's no significant changes in place. And one thing that you could also argue is that you could indeed do a lot of prediction in this kind of search engines databases, because it turns out that if one website, one page is changed in the past, in the future it will also be changed. So you have high predictability to actually understand that certain rows in the database will be changed in place because they changed in the past. But the majority of the changes in this database are going to be additions or removals. And on queries itself of the search engines, you will see that contrary to some other recommendation systems, on search engines, it seems that users are not so interested in concatenation of queries. So the majority of times, users query for 1 or 2 terms, and the mean is usually that they query for 2.4 terms. So you don't need a lot of ands. But they usually have several expectations depending on the type of query they launch. So sometimes on navigational queries, they actually want high accuracy responses. On informational queries, they want not so much accurate responses, but they want actually that those responses are kind of like from reliable sources. And there's also transactional queries. Navigational queries essentially means that a user is actually searching for a specific website. So for example, you heard that you want to buy some shoes, so you're essentially searching for that specific website that holds those specific shoes. Informational queries is when you're actually searching for information. And transactional queries are queries and that essentially you're launching to, for example, find a game and later do some dynamic operations over that specific website. And then around the amount of queries that, for example, systems handle, it is thought that Google processes almost at 8.55 billion searches per day. And usually how they use that is they use this specific distance that is called the TF-IDF. Okay, so that is great. And we have like kind of some information. What does this mean for PIR? One of the first things that I already kind of hinted to you about is that there's currently no research on PIR on this size of databases. So we have done some research on PIR on moderately sizes of databases, but these really big databases of the petabyte size have not been researched about. So we don't actually know how efficient PIR schemes are in regards with this specific size of databases. As you see here, we also have no research on actually what it will mean to put some of these PIR schemes with these databases that are highly updatable in their size. So we no longer care on databases that change in place, but rather that are added where elements are added or removed all the times. So if you want to create a PIR scheme that is efficient for these cases, you have to actually create a preprocessing phase that will allow you to also add rows to this kind of matrix representation of the database so that you could have a preprocessing phase. If not, maybe we will have to toss this preprocessing phase and always have online-only PIR schemes. We also have different user queries. So it doesn't seem that the users are so interested in actually have a batch of queries or an annual queries, but rather they are mostly interested in like 1 or 2 elements in that specific database. But accuracy seems to be crucial. So if you want to actually obliviously walk over that database, so you could find the nearest neighbors to that specific query, you want that specific comparison to be really accurate. So you return the specific closest element as you can to that specific query. The cost also remains to be analyzed because we don't know exactly how LWE-based PIR system will work with these sizes of databases. And if we don't have a preprocessing phase, how costly they will be. And again, what I've shown you is kind of the result of the research on like an old web. So this was our research from 2004, but the web has recently heavily changed with the introduction of Web3. So now we also have queries that are like interacting also with ML systems. We also have the ability to have a specific follow-up queries. So there's also an open research area in which we look also at these new search engines that exist. And the PIR systems will also work with those type of new search engines. Another example that we can look at is complex recommendation systems. So in the case of search engines, you usually are very complex, and trying to find the closest element to do your query involves a really complex algorithm, but you usually use some metric that is called the TF-IDF. Other kind of recommendation systems, on the contrary, use like other kinds of matrix or uses other kind of representation of the database. So for example, Spotify, as a music recommendation system, uses a specific algorithm that is called hierarchical navigable small worlds. What that this means is that you have like a graph representation of the database, in which what you can do is actually navigate that graph, that world, to actually try to find the specific element that is closest to your query. And they use a layer approach of this graph. So there's going to be a graph, but it has like different layers. So that is much more efficient to actually navigate that specific graph. If you're actually thinking already, how can we put this in PIR, you will see that this is very complex because indeed it will involve a lot of oblivious comparison over that specific graph structure. So no longer we will have to actually only get that specific element from the database, but rather we have to walk obliviously on the graph representation of the database to find the closest element to that specific query. Here, I already think that maybe there's some ways to actually be able to realize this in practice, because if you're familiar with the graph structure of all of these systems, you will know that graphs can be easily represented, both from an implementation perspective and mathematically, as matrix. And because of that, it maybe means that we could still use these LWE-based PIR schemes because we can reason on them, reason about this specific system in a matrix way. But we still need and have this open problem, this open gap, that we still need to do these oblivious comparisons. And if you're familiar with cryptography, you will know that doing these oblivious comparisons is not cheap. So we actually have to find a way in which we do this oblivious comparison. And then not only oblivious comparison in one layer, in one specific small world, but also on a layered small world. Here, maybe there's actually some hope, because it turns out that certain recommendation systems are much more able to handle updates, while others are not. So in the case, for example, that you have a system that gives you the latest news of the day and also recommends you the latest news, how does this system will behave is that you will construct this database every day, depending on the news that have existed that specific day. And that already takes an amount of computational time. Over that specific database that is now static because it only has all of the news of the day, maybe you could use PIR schemes that have this offline phase, because over the day they will not change and they don't incur much computational time when compared with the computational time that it took to create that specific database of the day. So for some of these recommendation systems that are targeted to, for example, be created on the day, maybe using LWA-based PIR is okay. But for other recommendation systems that hold a really big catalog, as for example, music recommendation systems that are also constantly updated, maybe again, we cannot use the PIR schemes. But we're starting the research on this, so there's some hope that we indeed will be able to handle these complex systems. Well, and to just like start to the end of the talk, essentially, as I've shown you, there's many ways and avenues that you can actually look like if you're interested in researching on PIR. Specifically expanding the security model, so we don't only work with public databases, but also with private databases. So we can actually have some techniques that allows us to handle updatable updates to that specific database. We also would like to see at other applications of database systems. Here I only talked about if you want to query for a single element or for recommendation systems, but maybe there's many more applications. Also, if you want to handle a database that has a variable length of elements, so think of databases as structured as JSONs. In JSON, the values associated with keys are more often than not of the single length. So in those cases, how can we actually represent them in this matrix structure of PIR? So we could also work with them. And can we also start looking at the state of the art of data structures, graphs of matrix theory? So we can see we could indeed take some inspiration from data structures and use us in our PIR research. So this is because when we actually did our research on the binary fuse filters, we actually found out that the majority of the good efficiency that we had on that scheme was because we were using the latest or the most efficient data structure, and we no longer were using only cuckoo filters. So I also encourage you that if you want to make something more efficient, maybe look at the data structure research, because they have made a lot of steps on making them even more efficient. And with that, I will give you some pointers of some of my favorite research papers. They are not saying that everything else is bad, but rather that these are my favorites. And I think these are foundational work that is going to help us to actually get PIR to other systems. And yeah, and with that, thank you very much. And I don't know if there are questions.
Thank you so much, Sofia. I really learned and enjoyed this talk very much. Let's give Sofia a round of applause. And maybe I can open the floor to questions. Otherwise, I have a few as well. Yeah? Yeah? Okay, you have the mic there. Yeah?
Hi, Sofia. It's Robin again. How are you doing?
Okay.
I just wanted to ask you, one of the applications of this kind of homomorphically encrypted query that I've seen proposed is for hash databases of child sexual abuse material, CSAM.
Oh.
Yeah. But from your presentation, I think I gathered that if the database in question grows rapidly, it may not be a particularly effective solution or approach. Is that correct?
Yeah. So in those specific types of databases, I think what they have more than not is that they have additions to the database rather than substitutions in place, I think. So in those cases, there is a way to actually expand the matrix representation of the database to also have like a new hint related to those additions, but it's not the most efficient way to do this. So in this case, we will still need to actually have a more efficient structure. There's some research on actually using some other techniques, so maybe those are much more leveraged for this specific case. But yeah, it is difficult to do updates when the database gets new rows.
So since I've got you here, what you described is all, so again, as I understand it, with classical homomorphic encryption, the principle is that the query is, well, essentially encrypted under a key that is owned by the client. Well, so for the CSAM use case, you want the result of that query to be returned to someone other than the client, in other words, to law enforcement or whoever. So does that fundamentally bend or break the system here?
Yeah, it will fundamentally break it because the assumption is that whatever you return is only able to be passed by the client, by the one that sent it, the query. Yeah, it will have to be a different system or expand the security notion.
Terrific, thank you. I'll try and explain that to some UK policymakers next week.
Hi, Sofia. This is Devajyoti.
Hello.
Hello.
Oh, hello.
I have a question. I have actually two questions. First question is, you mentioned about the PIR scheme with preprocessing. Also, the PIR schemes I'm familiar with, they also require some kind of preprocessing, and that means the client state is important. Client cannot be stateless.
Yeah.
So, in practice, if you want to support multiple devices for a user, or you want to allow the clients to be dropped, for example, you want to switch off your phone. In that case, do you see any future in the direction of single server PIR, or do we have to go to multi-server setting?
Yeah.
And the second question is maybe slightly different related. You mentioned about oblivious structures, oblivious operations implementation under for PIR schemes. Are you still thinking about LW setting? Because generally those operations are expensive and comes with a noise blow up.
Yeah.
So are you thinking still about LW setting, or are you thinking about moving away from LW? So these are the two questions.
Okay. Yes. So those are great questions. So for the first one, usually what you need for this single server lattice-based PIR scheme, crucially, is that you have a state on the server, and it's optional for the client to have this state. So in the cases of multi-device, for example, I will not recommend that much to have the client also have this state, because either you will have to send this state between the different devices, or also generate that state in those individual devices. So in these cases, it would be a little bit more complicated. But those are not crucial for the scheme. What is crucial is that the server has the state. And in regards to the second question, so one of the things that I put somewhere over here is that, yes, is that you could, in order to compute this oblivious comparison, what you usually do is that you compute different distances. And it turns out that homomorphically, by using LWE, you could perhaps do the Euclidean distance. And in this case, we're fine by using LWE. But let's say that you have a little bit of a more complex distance that you want to use in order to compare this query with another element in the database, so TF, IDF, or like there are many other ways to actually compute these. In those cases, there's not so much that you could use with the LWE-based systems. So in this case, I think we will have to maybe drop the lattices.
Okay. Thank you very much.
Do we have other questions? I have a question. So I know you said like we're a bit far from having PIR and search engines, but hopefully one day we'll reach that. What do you, like I'm really not from here, but like how do you do like the privacy evaluation, especially when it comes to search engine? Because a lot of times the fact that I am accessing a database, it's also, there is like a privacy leakage there. So let's be very positive and hopefully one day we'll reach this like, you know, PIR, amazing and search engine. What would be the other steps into achieving this world?
Yeah, it's true that usually if you, for example, contact a specific database, you could also, you are leaking the fact that you contacted a specific database. Or for example, in practice, these specific database systems of search engines are in such a way that they are like more efficient, right? And that means that certain servers are stored in certain geographical locations. Sometimes they are closer to the user. And the fact that sometimes you're pinging that specific machine that is closer to you could also reveal that your query is found on that specific subset of the server, of the division of the server architecture. So that can also be kind of like a privacy violation in itself. In those cases, I would love to also have it over some anonymity network. So that would be also one of my suggestions. But there's also quite a few works on actually thinking of these complex architectures of these database distributed systems. So we have only focused on actually preserving the privacy of the query. But what about if the databases are distributed on different geographical locations? What if certain subsets of those databases only have certain kind of information? Like that question also remains to answer of what kind of privacy violations we have when we have this distributed architecture of databases.
Okay, thank you. And unless we have other questions, let's give another round of applause. Thank you so much, Sofia, again.
Yes. Thank you
And
for having me.
yes, Sofia, hopefully next time we see you in person. Unfortunately, Sofia decided not to come for the political scene that is happening. But yeah, hopefully we see each other, whether here in the US or in Europe and in person, and we can continue this conversation. Thank you again.